ਤੁਸੀਂ ਇਸ ਪਰਸਨ ਦੀ ਸਹਾਇਤਾ ਕਰ ਸਕਦੇ ਹੋ? ਕੀ ਤੁਸੀਂ ਇਸ ਨੂੰ ਦੱਸ ਸਕਦੇ ਹੋ ਕਿ ਇਹ ਬਲਬ ਕਿਵੇਂ ਜਗੇਗਾ? ਹਾਂ, ਜਵਾਬ ਤੇ ਤੁਹਾਡਾ ਬਿਲਕੁਲ ਸਹੀ ਹੈ। ਇਹ ਬਿਜਲੀ ਨਾਲ ਹੀ ਜਗੇਗਾ। ਬਿਜਲੀ means electric current। ਅੱਜ ਦਾ ਇਹ ਲੈਸਨ ਸਾਨੂੰ ਇਲੈਕਟ੍ਰਿਕ ਕਰੰਟ ਬਾਰੇ ਜਾਣਕਾਰੀ ਦੇਵੇਗਾ।
Dear students, ਅੱਜ ਇਲੈਕਟ੍ਰਿਕ ਕਰੰਟ ਐਂਡ ਡ੍ਰਿਫਟ ਵੈਲੋਸਿਟੀ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਇਹਨਾਂ ਆਡੀਓ ਵਿਜ਼ੂਅਲ ਕਲਾਸਿਸ ਦੀ ਸੀਰੀਜ਼ ਵਿੱਚ ਅਸੀਂ ਇਸ ਤੋਂ ਪਹਿਲਾਂ ਰੈਸਟ ਦੀ ਸਟੇਟ ਵਿੱਚ ਚਾਰਜਸ ਬਾਰੇ ਪੜ੍ਹ ਚੁੱਕੇ ਹਾਂ। ਉਹ ਇਲੈਕਟ੍ਰੋਸਟੈਟਿਕਸ ਦੀ ਸਟੱਡੀ ਸੀ। ਕਰੰਟ ਇਲੈਕਟ੍ਰਿਸਿਟੀ ਦੀ ਇਸ ਯੂਨਿਟ ਵਿੱਚ ਅੱਜ ਅਸੀਂ ਮੋਸ਼ਨ ਵਿੱਚ ਚਾਰਜਸ ਅਤੇ ਇਸ ਦੇ ਨਾਲ ਜੁੜੇ ਵੇਰੀਅਸ ਇਫੈਕਟਸ ਐਂਡ ਫਿਨੋਮੇਨਾ ਬਾਰੇ ਪੜ੍ਹਾਂਗੇ।
Suppose two conductors charged to different potentials are supported on insulating stands. If they are held at a distance, there is no flow of electric charge from one conductor to another, though the potential difference exists between them. It is due to the fact that the charges on the conductors are separated by air, which is an insulator. If these charged conductors are connected by a metallic wire, it is found that there is a net flow of charges from the conductor at higher potential to the other at lower potential. The flow of charge continues till their electric potentials become equal. ਜੇ ਅਸੀਂ ਦੋਨਾਂ ਕੰਡਕਟਰਸ ਵਿੱਚ ਇੱਕ ਕਨਸਟੈਂਟ ਪੋਟੈਂਸ਼ੀਅਲ ਡਿਫਰੈਂਸ ਰੱਖੀਏ ਤੇ ਸਾਨੂੰ ਦੋਨੋਂ ਕੰਡਕਟਰਸ ਜੋੜਨ ਵਾਲੇ ਮੈਟੈਲਿਕ ਵਾਇਰ ਵਿੱਚ ਇੱਕ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਚਾਰਜ ਦਾ ਇੱਕ ਸਟੈਡੀ ਫਲੋ ਮਿਲਦਾ ਹੈ। ਕਿਸੇ ਮੈਟਲ ਵਾਇਰ ਵਿੱਚ ਇੱਕ ਫਿਕਸ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਫਲੋ ਆਫ ਚਾਰਜ ਇਲੈਕਟ੍ਰਿਕ ਕਰੰਟ ਕੰਸਟੀਟਿਊਟ ਕਰਦਾ ਹੈ। ਫਿਜ਼ਿਕਸ ਦੀ ਜਿਹੜੀ ਬ੍ਰਾਂਚ ਮੋਸ਼ਨ ਵਿੱਚ ਚਾਰਜਸ ਦੀ ਸਟੱਡੀ ਕਰਦੀ ਹੈ, ਕਰੰਟ ਇਲੈਕਟ੍ਰਿਸਿਟੀ ਕਹਾਉਂਦੀ ਹੈ।
We know that current carriers exist in solids and liquids as well as in gases. In today's class, we will discuss about the solid conductors only, in which the positive ions remain in fixed positions and the negative charges move to constitute the current. We will start by knowing the learning objectives of the lesson.
On completion of this topic, the students will be able to describe electric current, describe drift velocity, and derive a mathematical equation for it. Obtain a mathematical relation between electric current and drift velocity. Define mobility of electric charge carriers and deduce an equation for it. Define current density and write its equation.
The flow of charge in a definite direction constitutes the electric current, and the time rate of flow of charge through any cross-section of a conductor is the measure of current. That is, electric current is equal to total charge flowing upon the time taken, which is equal to Q by T if Q be the charge and T be the time. Consider both positive and negative charges to be flowing forward and backward, normally across a small area in a time interval small t. Let Q plus be the net amount, that is forward minus backward, of positive charge that flows in the forward direction across the given area, and let Q minus be the net amount of negative charge that flows in the forward direction across the given area in the forward direction in time t, is Q equal to Q plus plus Q minus. Whereas I hope you remember that I is equal to total charge flowing upon time taken equal to Q by T. If the value of Q is positive, then the direction of current is forward, and if the value of Q is negative, then the direction of current is backward. Sometimes the charges flowing normally through an area may not be steady, but varying with time, and then we can define the current like this. Let delta Q be the net amount of positive charge flowing normally across a cross section of the conductor in a direction in a time interval t and equal to t plus delta t. Then at time t, the current in the conductor is given by I is equal to limit delta t to 0, delta q upon delta t equal to dq upon dt, where dq upon dt is the first derivative of q with respect to time. If there are n charge carriers, each having charge E, across any cross section of the conductor in time t, then I is equal to Ne upon T. SI unit of current is ampere, denoted by capital A, where 1 ampere is equal to 1 coulomb by 1 second. Thus, the current through a wire is said to be 1 ampere if 1 coulomb of charge is flowing per second through a section of the wire.
As a matter of convention, the direction of flow of positive charge gives the direction of current. This is called conventional current. The direction of flow of electrons gives the direction of electronic current. The direction of electronic current is opposite to the direction of conventional current. So, in this diagram, if the electronic current flows from A to B, then the direction of conventional current will be from B to A.
It is also worth knowing that current is a scalar quantity. Let me now tell you about electric current in conductors. ਅਸੀਂ ਇਹ ਚੰਗੀ ਤਰ੍ਹਾਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਐਟਮਸ ਅਤੇ ਮੋਲੀਕਿਊਲਸ ਵਿੱਚ ਨੈਗੇਟਿਵ ਚਾਰਜ ਇਲੈਕਟ੍ਰੌਨਸ ਤੇ ਅਤੇ ਪੋਜ਼ਿਟਿਵ ਚਾਰਜ ਨਿਊਕਲੀਅਸ ਤੇ ਹੁੰਦਾ ਹੈ। ਇਲੈਕਟ੍ਰੌਨਸ ਅਤੇ ਨਿਊਕਲੀਅਸ ਆਪਸ ਵਿੱਚ ਇਸ ਤਰ੍ਹਾਂ ਬੌਂਡਡ ਹੁੰਦੇ ਹਨ ਕਿ ਉਹ ਫ੍ਰੀਲੀ ਮੂਵ ਨਹੀਂ ਕਰ ਸਕਦੇ। ਕੋਈ ਵੀ ਸਬਸਟੈਂਸ ਬਹੁਤ ਸਾਰੇ ਬਲਕਿ ਅਣਗਿਣਤ ਐਟਮਸ ਜਾਂ ਮੋਲੀਕਿਊਲਸ ਦਾ ਬਣਿਆ ਹੁੰਦਾ ਹੈ। ਕਿਸੇ ਕਿਸੇ ਮਟੀਰੀਅਲ ਵਿੱਚ ਤਾਂ ਐਟਮਸ ਬਹੁਤ ਜ਼ਿਆਦਾ ਕਲੋਜ਼ਲੀ ਪੈਕਡ ਹੁੰਦੇ ਹਨ। ਇਹ ਗੈਸਸ ਦੇ ਮੋਲੀਕਿਊਲਸ ਦੀ ਤਰ੍ਹਾਂ ਮੈਟਰ ਵਿੱਚ ਫ੍ਰੀਲੀ ਮੂਵ ਨਹੀਂ ਕਰ ਸਕਦੇ, ਪਰ ਇਹਨਾਂ ਦੇ ਕੁਝ ਇਲੈਕਟ੍ਰੌਨਸ ਫ੍ਰੀ ਰਹਿ ਕੇ ਇੱਕ ਐਟਮ ਤੋਂ ਦੂਜੇ ਤੱਕ ਫ੍ਰੀਲੀ ਮੂਵ ਕਰਦੇ ਹਨ। ਇਹਨਾਂ ਇਲੈਕਟ੍ਰੌਨਸ ਨੂੰ free electrons ਕਿਹਾ ਜਾਂਦਾ ਹੈ। These free electrons move under the effect of electric field. Of course, when the electric field is applied to it in a definite direction, resulting in a current in the material. Those materials which have a large number of free electrons and develop strong electric currents in them, when an electric field is applied, are generally called conductors. Materials like metals tap water, graphite, etc. are examples of conductors of electricity. ਕੁਝ ਮਟੀਰੀਅਲਸ ਇੱਦਾਂ ਦੇ ਹੁੰਦੇ ਹਨ ਕਿ ਉਹਨਾਂ ਵਿੱਚ ਇਲੈਕਟ੍ਰੌਨਸ ਬਾਉਂਡ ਰਹਿੰਦੇ ਹਨ ਅਤੇ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਅਪਲਾਈ ਕਰਨ 'ਤੇ ਵੀ ਐਕਸਲਰੇਟ ਨਹੀਂ ਹੁੰਦੇ। ਇਹਨਾਂ ਵਿੱਚ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਅਪਲਾਈ ਕਰਨ 'ਤੇ ਜਾਂ ਤਾਂ ਨੈਗਲੀਜੀਬਲੀ ਸਮਾਲ ਅਮਾਊਂਟ ਆਫ ਕਰੰਟ ਫਲੋ ਕਰਦਾ ਹੈ ਜਾਂ ਨੋ ਕਰੰਟ ਦੀ ਸਥਿਤੀ ਰਹਿੰਦੀ ਹੈ। ਅਜਿਹੇ ਮਟੀਰੀਅਲਸ ਨੂੰ ਇਨਸੂਲੇਟਰਸ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਫॉर एग्जाम्पल, wood, plastic, rubber, etc. are insulators. When an electric field is applied on a solid conductor in the shape of a cylinder or circular cross section, by attaching positively and negatively charged circular discs of a dielectric of the same radius as that of the solid conductor at the two ends as seen in this diagram. An electric field is set up in the conductor from positively charged disc towards negatively charged disc. Due to this electric field, the free electrons in the conductor are accelerated towards the positive disc side in order to neutralize the charges of disc. The motion of the electrons will be there till the electric field inside the conductor exists. In this situation, there will be a current for a very short time called the transient current in the conductor. If we apply a steady electric field in the body of conductor by connecting a cell or a battery across the two ends of a conductor rather than a transient current.
Drift velocity. A metal conductor has large number of free electrons or conduction electrons whose number density, that is, number of electrons per unit volume, is about 10 raised to the power 29 per cubic meter. These electrons at room temperature move at random within the body of the conductor like the molecules of a gas. The average thermal speed of the free electrons in random motion at room temperature is of the order of 10 raised to the power 5 meter per second. The directions of motion of these free electrons are so randomly distributed that the average thermal velocity of the electrons is 0.
If vector u1, vector u2, vector u3 unto vector un are random thermal velocities of n free electrons in the metal conductor, then the average thermal velocity of electrons is vector u1 plus vector u2 plus vector u3 plus unto vector un upon n, which turns out to be 0. ਇੱਥੇ ਨਤੀਜਾ ਇਹ ਕੱਢਿਆ ਜਾ ਸਕਦਾ ਹੈ ਕਿ ਮੈਟਲ ਕੰਡਕਟਰ ਵਿੱਚ ਕਿਸੇ ਪਰਟੀਕੂਲਰ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਨੈਟ ਫਲੋ ਆਫ ਇਲੈਕਟ੍ਰੌਨਸ ਜਾਂ ਚਾਰਜ ਨਹੀਂ ਹੁੰਦਾ। ਇਸ ਕਰਕੇ ਕਰੰਟ ਵੀ 0 ਹੁੰਦਾ ਹੈ। ਜਦੋਂ ਕਿਸੇ ਮੈਟਲ ਕੰਡਕਟਰ ਜਿਵੇਂ ਕਾਪਰ ਦੇ ਦੋਨੋਂ ਐਂਡਸ ਦੇ ਅਕ੍ਰੋਸ ਪੋਟੈਂਸ਼ੀਅਲ ਡਿਫਰੈਂਸ ਅਪਲਾਈ ਕੀਤਾ ਜਾਂਦਾ ਹੈ ਤਾਂ ਕੰਡਕਟਰ ਦੇ ਅੰਦਰ ਇੱਕ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਸੈਟਅਪ ਹੋ ਜਾਂਦੀ ਹੈ, ਜਿਸ ਕਾਰਨ ਕੰਡਕਟਰ ਦੇ ਫ੍ਰੀ ਇਲੈਕਟ੍ਰੌਨਸ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਦੇ ਆਪੋਜ਼ਿਟ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਫੋਰਸ ਐਕਸਪੀਰੀਅੰਸ ਕਰਦੇ ਹਨ ਅਤੇ ਨੈਗੇਟਿਵ ਐਂਡ ਤੋਂ ਪੋਜ਼ਿਟਿਵ ਐਂਡ ਵੱਲ ਐਕਸਲਰੇਟ ਹੁੰਦੇ ਹਨ।
During their passage, the accelerated free electrons experience frequent collisions against the copper ions or atoms and lose their gained kinetic energy. the free electrons are accelerated again after each collision due to the electric field towards the positive end of the conductor and lose their gained kinetic energy in the next collision. This implies that the extra velocity gained by free electron is lost in subsequent collisions. This process continues to take place till the electrons reach the positive end of the conductor.
If V is the potential difference applied across the conductor and L its length, then the magnitude of the electric field set up is given by E equal to V by L. The direction of this field in the conductor is from positive end of the conductor to its negative end, as you have seen. As you know, the charge on each electron is minus E. Each free electron in the conductor experiences a force given as vector F equal to minus E into field vector E. The direction of this force is opposite to the direction of field, which is clearly indicated by the minus sign. Now, if m be the mass of each electron, the acceleration produced can be given as vector A equal to minus E into field vector E upon m. Thus, under the effect of electric field applied, the free electrons have random thermal velocities and acquire small velocities by virtue of acceleration due to electric field with which they move towards the positive end of the conductor. These velocities are in different directions. So, each free electron describes a curved path between two successive collisions. As a result of it, the free electrons drift towards the positive end of the conductor with some average velocity called the drift velocity. It is defined as the average velocity with which the free electrons get drifted towards the positive end of the conductor under the influence of an external electric field applied. The drift velocity of electrons is 10 raised to the power minus 4 meter per second. If V be the potential difference applied across the ends of the conductor of length small l, the magnitude of electric field set up is given as E equal to potential difference per unit length, which is equal to V by L. इस इलेक्ट्रिक फील्ड ਦੀ डायरेक्शन कंडक्टर ਦੇ ਪੋਜ਼ਿਟਿਵ ਐਂਡ ਤੋਂ ਨੈਗੇਟਿਵ ਐਂਡ ਵੱਲ ਹੈ since the charge on electron is minus E. Each free electron in the conductor experiences a force vector F equal to minus E into field vector E. ਇੱਥੇ ਨੈਗੇਟਿਵ ਸਾਈਨ ਦਰਸਾਉਂਦਾ ਹੈ ਕਿ ਡਾਇਰੈਕਸ਼ਨ ਆਫ ਫੋਰਸ ਅਪਲਾਈਡ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਦੇ ਆਪੋਜ਼ਿਟ ਹੈ. If m be the mass of an electron, the acceleration of each electron is vector A is equal to minus E vector E upon m. इसे acceleration ਦੀ ਵਜ੍ਹਾ ਕਰਕੇ free electron thermal velocity ਦੇ ਇਲਾਵਾ ਇੱਕ ਹੋਰ additional velocity acquire ਕਰ ਲੈਂਦਾ ਹੈ ਜਿਸ ਦਾ direction electric field ਦੇ direction ਦੇ opposite ਹੁੰਦਾ ਹੈ. ਹਾਂ, ਇਲੈਕਟ੍ਰੋਨ ਦੀ ਵੈਲੋਸਿਟੀ ਵਿੱਚ ਗੇਨ ਬਹੁਤ ਥੋੜਾ ਹੁੰਦਾ ਹੈ ਅਤੇ ਉਹ ਵੀ ਆਇਨ ਜਾਂ ਐਟਮ ਨਾਲ ਹੋਏ ਨੈਕਸਟ ਕੋਲੀਜਨ ਦੇ ਦੌਰਾਨ ਹੀ ਖਤਮ ਹੋ ਜਾਂਦਾ ਹੈ. ਇਸ ਦਾ ਨਤੀਜਾ ਇਹ ਹੁੰਦਾ ਹੈ ਕਿ ਇਲੈਕਟ੍ਰੋਨ ਦਾ ਐਕਸਲਰੇਸ਼ਨ ਐਕਸਟਰਨਲ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਦੇ ਪ੍ਰੋਪੋਰਸ਼ਨਲ ਨਹੀਂ ਹੁੰਦਾ. ਪੋਜ਼ਿਟਿਵ ਆਇਨ ਵੀ ਇਲੈਕਟ੍ਰਿਕ ਫੀਲਡ ਕਾਰਨ ਫੋਰਸ ਦਾ ਐਕਸਪੀਰੀਅੰਸ ਕਰਦੇ ਹਨ ਪਰ ਹੈਵੀ ਅਤੇ ਮੈਟਲ ਵਿੱਚ ਟਾਈਟਲੀ ਬਾਉਂਡ ਹੋਣ ਕਰਕੇ ਆਪਣੀ ਜਗ੍ਹਾ ਤੋਂ ਮੂਵ ਨਹੀਂ ਕਰ ਸਕਦੇ. ਇਸ ਤਰ੍ਹਾਂ ਇਲੈਕਟ੍ਰੋਨ ਵਿੱਚ ਵੈਲੋਸਿਟੀ ਗੇਨ ਬਹੁਤ ਸ਼ਾਰਟ ਟਾਈਮ ਲਈ ਹੁੰਦਾ ਹੈ. The short time for which a free electron accelerates before it undergoes a collision with the positive ion in the conductor is called the relaxation time. It is denoted by the symbol tau. At any instant of time, the velocity acquired by electron having thermal velocity u1 will be vector v1 equal to vector u1 plus vector a into tau 1, where tau 1 is the time elapsed since it has suffered its last collision with an ion or an atom of the conductor. Similarly, the velocities acquired by the other electrons in the conductor will be vector v2 equal to vector u2 plus vector a into tau 2, vector v3 equal to vector u3 plus vector a into tau 3, and so on until vector vn equal to vector un plus vector a into tau n. The drift velocity is defined as the average velocity of all the free electrons in the conductor which get drifted under the influence of an external electric field applied across the conductor. It is denoted by vector Vd. Thus, for n number of free electrons, we can write vector Vd is equal to vector v1 plus vector v2 plus vector v3 and so on up to plus vector vn whole upon n. This can be written as vector Vd is equal to vector u1 plus vector a into tau 1 plus vector u2 plus vector a into tau 2 plus vector u3 plus vector a into tau 3 unto vector un plus vector a into tau n whole upon n. This in turn can be written as vector Vd equal to vector u1 plus vector u2 plus vector u3 and so on until vector un whole upon n plus vector a into whole of tau 1 plus tau 2 plus tau 3 so on until tau n divided by n, where tau is equal to tau 1 plus tau 2 plus tau 3 so on until tau n upon n. This is actually the average time that has elapsed since each electron suffered its last collision with the ion or atom of conductor and is called the average relaxation time. Its value is of the order of 10 raised to the power minus 14 seconds. As we know that the average thermal velocities of n electrons in a conductor is 0, that is vector u1 plus vector u2 plus vector u3 plus unto vector un upon n is 0. The equation for drift velocity becomes vector Vd is equal to 0 plus vector a into tau equal to vector a into tau. Putting the value of vector a in the relation that we had just written, we have average drift speed. Vector Vd equal to minus e into field vector e upon m into tau in terms of average relaxation time and electric field.
Relation between current and drift velocity. Here is a conductor, say a copper wire of length L and of uniform area of cross section capital A. Volume of the conductor is equal to A into L. If N be the number density of electrons, that is the number of free electrons per unit volume of the conductor, then total number of free electrons in the conductor is equal to A into L into N. If E be the charge on each electron, then total charge on all the free electrons in the conductor is equal to A into L into N into E. Let a constant potential difference V be applied across the ends of the conductor with the help of a battery. An electric field is set up across the conductor, and due to this field, the free electrons present in the conductor begin to move with a drift velocity Vd towards the left hand side as shown here. Therefore, the time taken by the free electrons to cross the conductor, that is T, is equal to L upon Vd. Since current I is equal to Q upon T, also equal to ALNE upon L by Vd. So, I is equal to ANE Vd. This equation gives the relation between the current flowing through the conductor and the drift velocity of the electrons.
Mobility of charge carriers, we are supposed to understand a new term known as the mobility of charge carriers, which is represented by symbol mu. This is defined as the drift velocity acquired per unit strength of the electric field applied across the conductor. Accordingly, it is mathematically given as mu equal to Vd upon E. If we substitute Vd equal to mu into E from this equation, in the equation I is equal to AN EVD, we get I is equal to AN into electric field capital E into mu E. This equation represents the relation between the current through the conductor and electron mobility. This equation also suggests that the SI unit of electron mobility is given as meter square per second per volt or meter per second per Newton into Coulomb. We still have one more term to be defined, that is current density denoted by vector small j. For a current I flowing through a conductor of cross-sectional area A, it is defined as J equal to I upon A. Since I is equal to AN E Vd, J is equal to N E Vd in terms of drift velocity and is equal to any square tau upon m into electric field E in terms of mobility and relaxation time. And now it is time to summarize the main points of today's lesson. If there are n charge carriers, each having charge E across any section of the conductor in time t, then I is equal to NE upon T. The equation I is equal to ANEVD gives the relation between the current flowing through the conductor and the drift velocity of the electrons. Mobility of charge carriers mu is defined as the drift velocity acquired per unit strength of the electric field applied across the conductor. Finally, let me ask you some questions before putting an end to this class. My first question is, define 1 ampere. The answer is 1 ampere of current is set to flow through a conductor when 1 coulomb of charge flows through it in 1 second. My next question is, what is the expression for current density in terms of drift velocity? Answer is, in terms of drift velocity, the current density J is equal to NE into VD. मैनू उम्मीद है कि तुहानू अज दा ये टॉपिक ना केवल दिलचस्प ही लग्या होवेगा बल्कि यूजफुल भी लग्या होवेगा। ਲੈਸਨ ਦੇ ਕੰਟੈਂਟਸ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਧੰਨਵਾਦ। ਇਸੇ ਤਰ੍ਹਾਂ ਇੰਟਰਸਟਿੰਗ ਟੌਪਿਕਸ ਨਾਲ ਅਸੀਂ ਹਾਜ਼ਰ ਹੁੰਦੇ ਰਹਾਂਗੇ। ਅਗਲੀ ਕਲਾਸ ਤੱਕ ਆਲ ਦ ਬੈਸਟ।